Okay, so welcome everyone. Thank you for coming to the webinar. So before I introduce the speaker and we move on with the talk, let me just say two things. So the first is that please use the chat box if you have any questions in between the talk. Just use the chat box and I'll put the question to the speaker either at the end, or if the question is very important, then during the talk as well. And the second thing is, if for some reason you get disconnected, then you can also watch the video on our Facebook page. I'll share the link of the video, so you can go there and just drop me an email if anything happens during the talk. Let me welcome our speaker today, Dr. Bhupen Deka from IIT Guwahati. So Dr. Deka is an associate professor in the Department of Mathematics at the Indian Institute of Technology, Guwahati. Before joining IIT Guwahati, he was at Assam University for a brief period of time, and then at Tezpur University, where he was my teacher, and he taught me the first analysis and ODE courses, which were very nice. I still remember the classes. Dr. Deka did his BSc from Cotton College, MSc from IIT Delhi, and PhD from IIT Guwahati. And his research interests are in numerical analysis, finite element method, and interface problems. And today he's going to speak about existence, uniqueness, and stability of solutions for IVPs. So thank you, sir, so much for giving your valuable time. Please, sir, you can start the talk.
Okay, so thank you, Monjil, for your nice introduction. So I welcome all of you to my presentation, so which I'll be speaking on existence, uniqueness, and stability of solutions for initial value problems. So the objective of my lecture is to realize the fact that differential equation is not a course. So where you will give a equation and then some formula and you will get a solution. So it is actual differential equation, you will not have that much flexibility. So when you really want to start a course on differential equation, so it has a relation with linear algebra, functional analysis, and then if you wish to apply somewhere, then you have to be very good in computation also later on. So I'll start with a very basic question. So what is a differential equation? So differential equations means, so any equation which involve the derivative, so that we'll call as a differential equation, right? So more precisely, if you consider a ordinary differential equation, then you will have a independent variable, say x, and then you will have a dependent variable y, and then you will have a mathematical relation involving x and all possible derivatives of the dependent variable y for some x belongs to AB, right? So now this definition one can make more precise, just introducing a mathematical term that is called the order of a differential equation. So what is the order of a differential equation? That is the highest derivative which present in the equation that you call a order of the differential equation. So that gives me a nice formula for a nth order differential equation. So which is given by equation 1. So nth order differential equation involving x as a independent variable and y as a dependent variable can be given by a mathematical relation involving x, y up to the derivative of order n for x belongs to AB, and where y dash, y double dash are all the traditional notation to denote the derivative, right? So basic idea of a differential equation course is to find out some function y which basically satisfy the equation 1. So that is the main idea. So now if you see the properties of y, then you have to deal with the derivative. And y is a function which will deal with the derivative all those solutions. So more precisely, you have to deal with some function spaces. So when you talk about the derivative, then the naturally comes to in your mind that what type of function space that you need to deal with. So naturally, you will start with the basic classical finite classical function space that is known as CAB. So what is CAB? It is the collection of all continuous functions. defined in the interval AB. And then CAB is, you can add some operation over the collection of continuous function, but naturally, that means if f and g are some continuous function, then you can define the addition between two functions by f plus z, and f plus z is also a function which basically map at x to fx plus z of x. So now if you see the notation wise, there is a difference between the notation f and fx. So when you are writing f, then f is basically denote the function, and when you are writing f of x, it basically represents a real number. So in other sense, you have to deal with two sets, namely the collection. That means you have to deal with two sets, namely the a function which belongs to CAB, and then the set of real numbers. So that you also, because f is a function, then fx is a real number. So naturally, you have to deal with two sets, CAB and R. So to distinguish between them, we call the member of CAB as a vector and the member of R as a scalar. And once you define the scalar and vector, then that gives me a flexibility to define the scalar multiplication of our function. So if C is a real number and F is a continuous function, then CF will be another function which will be defined in CFX is equal to CFX for all x belongs to AB, right? So now, once you do that, then this gives me a nice structure of CAB. So what are the structure you can talk about? You can talk about the zero element of CAB, and naturally what will be the zero element of CAB? That will be the zero function. So what is zero function? 0x equal to x for all x belongs to AB. And then one can see that there is a difference between zero. There are two zeros. One is 0x and right hand side another 0. So when you are writing y equal to 0 and yx equal to 0, then there is a difference. So y equal to 0 means y is a zero function, and when you are saying yx equal to 0, so that tells you a y, that is a real number. That means value of y at x, that is equal to 0, and that is purely a real number. So then this gives me another the important element of CAB, that is known as identity element. So what is the identity element? So identity element is nothing but the identity map. So which map x to x, that means I of x equal to x for all x belongs to AB. And with this operation, basically one can prove that CAB is a vector space, and with the 0 as a zero function and identity as a identity function. So once you have CAB as a vector space, and then you can derive each all that means subset C1AB, which is the collection of continuously differentiable functions. And then, so similarly, twice continuously differentiable functions are denoted by C2, and C1, C2 both are subset of CAB. And one can easily say it is not only a subset, these one can easily verify that these are the subspaces of CAB, right? So now you in the structure you will have CAB is a bigger space, and C1AB is a smaller than CAB, and C2AB is further smaller than C1AB, and this inclusion basically goes in that way, right? So more precisely, all these spaces are vector spaces, and the operation that already we have defined. So now let us come back to our original equation. So first order equation. So what is a first order equation? So it is a mathematical relation involving x, y, and y dash x. So for x belongs to a, b, right? So now what is y? Y is basically a function. So how you will characterize? So y is a function of x which satisfies this equation 2 for all x belongs to AB. So that means if you have a function which satisfies this equation for all x belongs to AB, then you will call that as a solution, right? So solution means, solution to a differential equation means it is a function which satisfies the given equation for all x belongs to AB, right? So now, since you are expecting that your solution should be well defined for all y, for all x, as well as its derivative should be defined for all y dash x. So naturally it is expected that your solution y has to be continuously differential. In other sense, your solution y is continuous and y dash both are actually a continuous function. So y and y dash both are continuous functions means they are basically a continuously differentiable function. That means y belongs to C1 AB. So formal definition of a solution to the equation 2 will be read as, so a continuously differentiable function y which satisfy the equation 2 for all x belongs to AB. And such solutions are known as a classical solution. So classical solution means any function which satisfy the given equation at all the points is called as a classical solution, right? So now, so once you have the definition of classical solution, suppose y is the classical solution. So y classical means it has to be C1 AB. If it is classical, then it will satisfy this equation for all x belongs to AB. Then natural question arises, so how do you get y? Because our objective of a differential equation course is to find y. So how to get y? Naturally, somehow you have to get rid of the derivative of y. So if you can have a get rid of the y, then basically that will gives you a expression for y. So now in this case, if you are expecting to get rid of the derivative of y, so first assumption is that you should able to solve this equation 3 for y dash x. So if you are able to solve this equation for y dash x, so that means y dash x can be written as a function of x and y of x. So that clearly written as for the equation 4. So that means y dash x is equal to f of xy for x belongs to AB. So that means if you are expecting to solve this equation 3, then you are assuming that you can solve it for y dash x, and then this y dash x, once you solve, that will gives you a equation of the form y dash equal to f of x comma y, x belongs to AB. So now once you have this y dash x, then you can find out y simply by integrating in some interval. So here I am integrating the equation from a to x. So that gives me a expression for y of x that is given by equation 5. But the problem is that this is not the solution of this basically is not the expression of the solution. Yes, it is an expression of the solution, but it cannot explicitly give you the solution because you are expecting to solve this equation. That means you are going to find out y in terms of x. Now what happens once you integrate, that gives me expression yx equal to ya plus a to x f of s y as d of s. But this y is unknown. So that means this yx cannot be find out explicitly by the equation 5. So that means this equation has shown no general formula to get a solution. That means directly you cannot say that this equation has a solution of the form. That means there is no closed form solution. So now we need another tool. So simply solving for y dash x, then integrating over the interval a to x may not serve your purpose because that may not gives you a explicit form of the solution. So you need another tool to further simplify your first order equation. So once you wish to further simplify your equation, then it's turned, that means you have to write down the equation in an operator notation, and through some basic definition of linear algebra that can be used to simplify your equation. So suppose y is a solution of this equation. So now once you have this y as a solution, then you can relate this differential equation with some operator. So what is that operator, that I'll come later. But if you see that simply what I am writing tyx is equal to the whatever the expression you have. So whatever the differential equation you have, that you are writing in a different notation, like tyx is equal to f of x, yx, y dash x, and that for all x belongs to AB. So now for the notational convenience, so now you see that what is tyx. So for given x, the right hand side is a real number. So since it is a real number, so it's for each x, tyx is a real number. So if tyx is a real number, then what about ty? So ty is nothing but a real valued function from AB to R, because x is coming from AB. So ty is a real valued function defined in AB, right? So if ty is a real valued function, then what is t? So
Sir,
t.
sir, sorry to interrupt. There is a question
Yes.
somebody is asking, why is f x y x y prime x a real number?
Where?
Um, so you mentioned that f is a real number. So why is f
Mm-hmm.
a real number?
Oh, no. That is basically in throughout my lecture, I will be talking about only the real valued functions.
Okay, sir.
Only I will be talking about the real valued function. That means whatever the coefficients and other things will be coming up, all will be real valued.
Okay,
So
sir.
capital F is a real valued function.
Okay, sir.
Okay. So what is t? T is basically a function that more precisely we call as an operator defined on a real valued function y, which is y, and that is basically y is a C1 which is defined in the AB. So now the clearly domain of the space T is a C1 AB. So that means T is operating on y. Again, y is a solution to this equation. Solutions means it belongs to C1AB. So T is a operator which is acting on C1AB. But what is the range? So naturally, if you see this Tyx, so if you treat Ty is a function which is well defined for all x. So that means you are expecting that this expression should be well defined for all of x. So that means for each x, this quantity should be well defined. So naturally, what we expect that this function Tyx, so whatever the outcome will come in terms of a function, that one can expect to be a continuous function. So more precisely, we assume that this first order equation in an operator notation can be represented as a operator T from C1AB to CAB, and CAB is already we have mentioned collection of all continuous function. So this equation now one can write in terms of the operator. So T is going from T1AB, sorry, C1AB to CAB. So Ty is defined by this map, and what is this map? That is coming from the given equation. So that means in other sense you are converting a differential equation to a operator. So that operator is basically the T, right? So now this is our the operator T, and then this gives me a opportunity to define the linearity of the given differential equation. So what is the linearity? So that means this is our given differential equation 7. So now this differential equation 7 is said to be linear provided that operator T is linear. So already the operator T is defined. So if T is linear, then you call that this differential equation is a linear equation. So now if you recall from the linear algebra, then the operator T from a vector space C1AB to another vector space CAB is said to be linear provided it satisfies these two conditions. So linear means Ty1 plus Y2 is equal to Ty1 plus Ty2, and Tcy is equal to Tcy for all Y1 belongs to CA1AB and the scalar C belongs to a real number. So now if you relate this definition with our differential equation, then that naturally gives you. So now by definition, that for all x belongs to this, then Ty1 plus Y2x, by definition, it will be f of x, y1 plus y2x, y1 plus y2 dash x. So this is from the definition of operator T. And similarly, T Cyx is equal to f of x, cy at x, comma, cy dash x. So these two, they are coming from the purely from the definition of the operator T. So now, if you use that f to be linear, that means T has to be linear. So if T is linear, then applying this definition, what you will get? Ty1x plus Ty2x, and this one will gives you C into Tyx. So if you apply the linearity of T, so that gives me a condition on f. So that tells you f of x, this one is equal to written as Ty1x plus Ty2x. Again, apply the definition of Ty1 and Ty2, that gives you this expression plus this, and similarly the other one will gives you the other relation. So what it tells you, that means f is said to be linear provided for each x f is linear in yx and y dash x. And this definition holds true for the other higher order differential equation also. So that means if you are dealing with a second order equation, say f of x, y dash x, y double dash x, so then f is said to be linear if for each x, f is linear in yx, y dash x, and y double dash x, and you can continue with the higher order differential equation also. And not only in case of ordinary differential equation, same definition holds true for a partial differential equation also. So that means linearity of a differential equation means the equation has to be linear in the solution and its possible derivatives, right? Okay, so now one can easily check that equation A, this equation and these equations both are non-linear. That means first one can see that it cannot satisfy. Suppose if I replace y by cy, then this will give me cy and then cy dash x. That cannot be equal to c into f of x, y dash x. So that means the linearity will break due to the fact that yx and y dash x are there. And similarly here, straight away I can say that yx is not linear. That means yx square is there. So straight away one can say that this is not a linear differential equation. And most of the textbooks, it's right that a differential equation is said to be non-linear if it is a product of yx and y dash x and so many conditions. But those are basically a derivation from a basic definition. So one should not use those condition as a definition. So definition means the operator which are associated with the differential equation, that has to be linear. If it is linear, then the equation is itself is a linear differential equation. That's all. The rest of are the corollaries or the consequences of the basic definition, right? Okay. So now let us move to the first order linear differential equation. So what is first order equation? It is a mathematical expression given by equation 9. So now what is linear? So linear means f has to be linear in yx and y dash x. Since f is linear in yx and y dash x, so naturally it should be of the form ayx plus by dash x plus c equal to 0. So now once you apply this definition, then it could be written as something like that. So that means AF is said to be linear if it is of the form that y dash x plus pxy equal to qx, x belongs to AB, and pq are assumed to be a continuous function in this case. And then you know that using the integrating factor, you can write down the solution of this differential equation by equation 11. So now one can easily see that means if P is continuous, Q is continuous, then R is straightaway continuous because it is the integration of a continuous function. Then the integration of ut and then multiplication of continuous function, this will be continuous. So all this quantity will be well defined. So that means if your given functions, coefficient function as well as source function q are continuous, then straightaway one can see that the expression given by 11 gives you a classical solution. That means that this equation, linear equation, has a classical solution if p q are continuous, right? And the solution has a explicit form. That means your solution can be written in terms of the given function. So that means if p is given, q is given, then one can have a closed form solution of the linear differential equation. So which was not the case in case of a non-linear differential equation. So in case of non-linear, even your data are given, but you cannot find out the solution, right, explicitly. But in linear, you can find out the solution explicitly. So now, so this again tells you that you will find out the unique solution of this equation provided this ya is supplied to you. So if ya is supplied to you, then such type of problems are known as a initial value problem. So more precisely, a initial value problem, linear initial value problem, will be governed by a differential equation and along with a condition at a point x naught. So 12 together is known as a initial value problem, and pq are given to be a continuous function, right? Okay. And then the solution is given by this form So by using the integrating factor, then the solution is given by this form because your initial data is given by this form, right? So now one can say that if PQ are continuous, then solution given by 13, that means solution is this, given by 13 belongs to C1 and it satisfies the initial value problem for all x belongs to AB. And then you can realize that if you q that right hand side q function is 0 and your data is 0, then from this expression, so q 0 y not 0, then this expression will be become 0. So that means q 0 y not 0, that gives you that y x is equal to 0 for all x. So yx equal to 0 for all x means, that means y is equal to 0. So that is a zero function. So this means, hence, continuity of P and Q are sufficient for the existence of a unique solution. So this observation this tells you that if PQ are continuous, then this gives you a unique solution, and unique solution follows from this fact: y equal to 0. If Q is equal to 0, y not equal to 0. Because if you assume that 12 has a more than one solution, suppose y1 is a solution, y2 is a solution. So y1 solution means y1 dash x plus px y1 x equal to qx, and y1 x not equal to y naught. Similarly, y2 will satisfy similar set of conditions. So you subtract. When you subtract, then right hand side q minus q will be 0 and data y naught minus y naught will be 0. So that means you will end up with a differential equation of the form y1 minus y2 dash plus p y1 minus y2 is equal to 0, where q is equal to 0 and data is 0. So using this fact, one can find y1 minus y2 will be 0. So that will gives you y1 equal to y2. So therefore it said that if your given functions p and q are continuous, then it is sufficient to ensure that this initial value problem has a unique solution. So if your given functions are continuous, that ensure the uniqueness of a solution of equation 12. So now here, apart from existence and uniqueness, I have made one another point. So that is called as the that means stability. So that what do you mean by stability? So stability is related with the round of error. So how round of error plays the role? So let me explain. So you just consider a very simple equation. Y dash x is equal to 1, y0 is equal to pi. So that is very simple equation and one can easily verify. That means yx equal to x plus pi is a solution to this differential equation. But when you wish to find out the value of the solution at a particular point, so that will depend on the value of pi. But you already know that pi is a notation. So pi is a notation, and what is the value of pi? Pi is given by 3.14, and then it is the non-terminating decimal point you will get. So that means there is no end of those dots. So now it's clearly, when you wish to find out the value of the solution at a particular point, that clearly depend on how much memory you have. So for example, if you say, so what is the value of pi? Then immediately I'll say that pi is 3.14. And someone has a better memory, then he will say that for me pi is 3.141. And if you ask Professor Noyandip Dakabura, he may go for some more digits. In fact, I do not remember. So he may go a very maybe 30-40 digits he can recall. So it's purely depend on the memory, that how much digit you can basically memorize. So now for me, that means pi will be 3.14. So when you substitute pi is equal to 3.14, then that gives me a solution which is given by x plus 3.14. But x plus 3.14 is not the actual solution, because actual solution is x plus pi. But pi is not equal to 3.14. It is only the rounding you are doing. That means pi is rounded to 3.14 and you are writing. So that means whatever the solution you will get, that is different from the original solution y. So that is given by y1x. And then similarly, pi, someone has a better memory, so you will write pi is equal to 3.141, and then you will get a different solution, say y2x, that will be given by x plus 3.14. So that means depending on your memory, you are basically solving a different initial value problem. So now, when you have a influence of round up error, that means your data, what was the data? Your data was pi, so that initial value has been shifted to some another value that you are calling pi delta. So delta is basically a parameter associated with the round up error. So you are solving a different initial value problem, that is y dash delta is equal to 1 and y delta 0 is equal to pi delta. And the solution of this equation is given by, so x plus pi delta. So now what do you mean by stability? Stability tells you that if your round up error is very small, that means if pi delta minus pi tends to 0 when delta tends to 0, that means if you can neglect, you can make the round up error arbitrarily small, then you can expect that the difference between y and y delta, that will be negligible. So that means the perturbation of your given data should not influence the your solution. So that means if your perturbation is very small, then accordingly you can expect the small perturbation in the solutions, right? So that exactly tells by this notation. So this tells you if pi delta minus pi tends to 0, then y minus y delta will tends to 0. So you can, in this case, this is known as the stability. And then let us come back to our
Sir,
problem that whether, sorry,
sorry
yes.
to interrupt. Before you move on, there is a question from 2 slides back. If you can go
Okay.
2 slides back. Yes, sir.
Hmm.
So the question is, how did we say that the solution is C1 in this case?
Well, okay. So now you just take e to the power x to the right hand side. So e to the power minus x, that will always remain to be a continuous function. So you can differentiate, because ultimately what you will have. So you will have, so e to the power minus x in the right hand side, then multiplication of this. But this function is a differentiable function, because q you have assumed continuous, then e to the power rt, that is again to be a continuous function. So under the integration sign, by fundamental theorem, that has to be differentiable function. Again you will have a e to the power minus x, that will be anyway differentiable, and then y naught, that is constant, into e to the power minus x, that is a differentiable function. So ultimately that will be given to me a continuously differentiable function. So here I did not written down explicitly, so just to take e to the power x to the right hand side, that's all. That way you write, that means in your textbook it's described. So yx equal to e to the power minus rx into this plus y naught into e to the power minus rx. So is it okay, Manjil?
Yes, sir. Thank you.
So it is basically the multiplication of two differentiable function, and that function satisfy the original equation. That's all, right? Okay, so can I move ahead?
Yes, sir. Yes.
Okay, okay. Okay, so now what do you mean by stability? Stability means it is a mathematical term that is used to describe the perturbation of the problem. So if you have a perturbation of your given data and that perturbation is small, then you can expect a small perturbation in the respective solutions also. And that exactly known as the stability, and it is defined by this. So if your initial data tends to 0, then you can expect that this difference will also tends to 0, right? So that is stability. So let us see whether our initial value problem is stable or not. So now from the definition, so you have y dash x equal to 0 and y delta dash equal to 1. So you subtract. When you subtract, that will gives you y minus y delta dash equal to 0, and with this value. So y minus y delta at 0 equal to pi minus pi delta. So since derivative is 0, it has to be constant function, and since a value of this function is prescribed by pi minus pi delta, so you will have y minus y delta x equal to pi minus pi delta. So one can clearly see that in the difference between y and y delta for all x will be bounded by pi minus pi delta. So that means if pi minus pi delta is negligible, then 1 minus y delta will be also negligible. In other sense, if this difference is small, then this difference will be automatically very small. So that means our initial value problem that you have considered is a stable initial value problem. So now the stability tells you something else. So that leads to some well-posed problem. So what is well-posed problem? So that is defined by Professor Hadamard, a French mathematician, who says that since differential equation is a course which are used to solve a practical problem, real life problem, and that mathematical model which you are deriving from a real life problem, that should have a solution. And that solution should be unique since it describes a physical problem. And apart from that, he adds one more criteria, that means the solution should continuously depend on the given data. So that means this third condition is nothing but the stability. So that in modern version, it is known as a stability. So stability along with existence and uniqueness, that is known as a well-posed problem. So why well-posed problem is so important? It is important because the real life problem, the model you are proposing, that may not be solvable manually. So you may not able to solve that model manually. So you have to solve by some numerical scheme. And then when you are applying a numerical scheme, towards the end, you expect that your approximation should converge to the exact solution, right? So now therefore you need all these three. So I say that a solution exists to a differential equation is very fundamental. Why it is fundamental? Because if the problem doesn't have a solution, then why you should break your head? So that means if the problem is no solution, that means just leave it, forget about that problem. So first of all, it should have a solution. Then why the solution should be unique? As I said, that all the mathematical model are solved by some numerical scheme. And when you are solving using a numerical scheme, you expect that your solution, approximate solution, should finally converge to the exact solution. So now already you know, if you have a convergence sequence, then limit should be unique. Now if you have a convergence approximation, that will give a unique limit. But if the problem has a more than one solution, that means now there is a confusion that through your approximation, you will not able to capture all the physical properties of your problem. So in other sense, before applying a numerical scheme, one has to make sure that the solution is exists, then the solution is unique. Then you can go for the numerical scheme. Then the third condition, the solution should continuously depend on the given data. That tells you that ultimately whatever you are approximating, so that ultimately solve in a finite dimensional setting. And finite dimensional setting means that is nothing but a system of equation. So that system of equation also should be free from round up error. So that means although theoretically your problem is convergence, but ultimately when you apply some solver, that solver should also free of your round up error. So that exactly given by three conditions. So a solution exists, that is quite fundamental. The solution is unique, so that you need to preserve the uniqueness of the limit of your approximation. And then the third one is basically your computation should be free from the round up error. So these three are proposed by Professor Hadamard. And if a problem, mathematical problem, has these three properties, that you call a well-posed problem, right? Okay. So now let us move to a higher order problem. So here I have considered a very simple initial value problem. So I'll consider a kth order differential equation. So that is given by equation 17. So where all those coefficient function p, k minus 1, p1, p naught, and this source function q, all are continuous fixed function defined on a, b, and along with a set of initial conditions. So since it is a kth order equation, so this will have a unique solution provided kth initial conditions are given. So here at a particular point C, you are giving some initial conditions. So yc is equal to alpha 1, y dash c is equal to alpha 2, and dot dot dot. So what do you mean by stability of this initial value problem. So your given function is Q, and then your initial values are given by a matrix. So that is alpha 1, alpha 2, alpha k. So these are the initial data. So and for Q is the given function. So you can describe the stability by saying that if your data is very, the perturbation of your data is very small, then the corresponding solution, perturbation of the corresponding solution will be very small. So before going to 17, I will give you the proof for this 18. So similar technique you can apply to solve with the general initial value problem, this higher order initial value problem. To motivate, I'll consider a first order equation, and the condition is given by yc is equal to alpha, and p, q all are continuous function, and alpha is a real number. So then already I said that there will be always influence of round up error. So due to influence of round up error, your given data alpha, that will be perturbed to alpha delta. So accordingly, you are solving a different initial value problem. The solution of the initial value problem is y delta. So y is the actual solution, and y delta is the solution of the perturbed problem due to round up error. So now, so what do you mean by stability? So stability means the same definition. So that means if this difference tends to 0, then y minus y delta tends to 0. So that means this gives me that gives me to idea that you have to measure the distance between y and y delta. So you need a tool to measure the difference between y and y delta. But what is y and what is y delta? Y is a function, y delta is again a function. So their difference is nothing but mod of y minus y delta, if you go by the notation of real numbers. But mod of y minus y delta is not a real number. Mod of y minus y delta, it is a function which is defined by this equation. So that means mod of y minus y delta x equal to mod of yx minus y delta x. So which is basically based on the difference between the distance between two real number yx minus y delta x. So yx is a real number, y delta is also a real number. So that means this mod of y minus y delta, this will that if you ask yourself that whether is it represent the distance between function y, so no, not exactly. Why? Because this is a function, and since it is a function and distance is measured in terms of a real number, so not exactly mod of y minus y delta can gives you the distance between two functions. So now what we do, we try to generalize the concept of mod in R. So if you remember, then distance between 2 points in R is measured by the mod function. So now we wish to copy the properties of mod function to the general vector space. So here we are going to discuss the copy the properties of this mod function over the C1 CAV, so that you can define the distance between two functions. So now these functions, if you see that what are the properties, so to that properties you just see if x1 is a real number, x2 is a real number, then the distance between these two are defined by mod of x1 minus x2, and these satisfy this triangle inequality and this property. So that means the distance between 2 points are defined by mod function, and what is mod function? This is given by this, and it satisfies certain properties. So that may measure property the triangle inequality. So now we wish to copy this property to a general vector space. So what we have a tool. So we have a tool to measure the distance between 2 points in R, and that tool we wish to generalize to define the distance between two functions, two continuous functions. So to do that, we have to generalize the notion of that means notion of a magnitude. So how to generalize? It is generalized by a real valued function denoted by this symbol, and it is called norm, and it satisfies certain conditions, satisfied all the distance. That means your mod function. That means norm of x is greater than equal to 0. If x is 0, then x has to be 0, then this linearity property, and then the triangle inequality. So all those properties are satisfied your mod, that means your mod function, and that we have generalized for a general vector space capital X over the R. So now this any vector space equipped with equipped with this magnitude, which you will call norm, is called as a norm-linear space. And in fact, a norm-linear space is nothing but a metric space. So how it is a metric space? If you have a norm-linear space, so this gives you a distance between two vectors. So if x is a vector, y is a vector in capital X, then the distance between these two vectors is defined by norm of x minus 1. And then one can easily check that this basically actually define the properties of distance. So if you have a norm, so that norm will gives you a distance, and so that ultimately gives you, if a non-linear space, that will be a metric space also. So this idea one can use to define the distance between two functions, continuous function. So in order to define the distance between two continuous functions, so what you need? So you need a norm. So through that norm, you can define the distance between two functions. So now you just see that two continuous functions f and g, and then f is given by, say, this one, and g is given by the red line. So now a red curve. So now the distance you can measure by mod of x minus g of x for a particular x. So when you talk about the distance between the function f and g, immediately it comes to in our mind that for a particular x, mod of f of x minus g of x will gives you the distance. But that questions come, so whether this definition can you generalize, which basically capture all the points. So that means in order to capture all the points, so what we can define, that means I can define maximum of mod of f of x minus g of x. So that means it tells you that rather than calculating at each value of this distance, you just calculate the maximum of that difference. So, and in fact, this will gives you a difference between f and g, provided these distance are generated from a norm. And in fact, one can associate this distance by a norm that is called as a infinity norm or supremum norm. So how it is defined? If f is a continuous function, then the magnitude of f is defined by infinity is equal to maximum of x belongs to AB, and then this gives you a distance between the two functions f and g. So if you define the magnitude over CAB by this formula, that will gives you a distance between function df comma c, and which will given by maximum of fx minus g of x. So that means, so if you wish to measure the distance between two functions, so we have a tool to measure that. So how we'll measure? We'll measure by this formula. So that means you find out the distance between two at a particular point, and you continue over AB, and then you try to find out the maximum of this. So that will gives you a distance between these two. So for me, the distance between two functions will be calculated by these two formula. That means maximum of x belongs to AB, fx minus g of x will be the distance between two functions, f and g for me, right? You can define other distance also, but for in this presentation, I'll only concentrate on this distance, right? Okay. So now you come to this CAB infinity. So this is actually a non-linear space, and this gives me a no distance that is given by D. And then next questions come from the fact that since it is a metric space, so can you talk about whether all the Cauchy sequences are convergent? So this leads to a complete metric space, and then a complete non-linear space is a Banach space. So that means the moment CAB become a metric space, you check that whether all Cauchy sequences are convergent. If it is convergent, that is known as a Banach space. And these Banach space are due to the Professor Stefan Banach, a Polish mathematician, and who is known to be the father of the functional analysis. So due to him, all those spaces and functional analysis we are discussing. And for us, in CAB, the distance will be measured by these two, right? So now, similarly, one can continue this concept of magnitude over C1AB. Then, in fact, you can discuss the magnitude over the product spaces. So C1AB is also a Banach space given by this notation. So that means f1 infinity is equal to f infinity plus f dash infinity, and then Similarly, CKB will be also a Banach space given by this norm, that means given by this magnitude, right? So then this product space CAB. So what is CAB? It is nothing but the Cartesian product of CAB cross R. So that means it will have a pair of elements. So that means it will be something like F comma alpha. So where F is coming from the space CAB and alpha is coming from the real number and F is coming from CAB. So you can define a norm over F. So that is the supremum norm. That is the infinity norm. And then mod, that means magnitude of R is nothing but mod of alpha. And this can be defined for all F belongs to CAB and alpha belongs to R. And in fact, one can see that this also a Banach space. So what we have, so C1AB is a Banach space, then the product space CAB cross R is also a Banach space. And the norm over CAB is given by C1AB is given by this, and norm over CAB is given by the infinity norm. Now how this is related to our discussion. So that is the natural question, that why we have from the differential equation to functional analysis, why we have moved that. So because if you have seen that already for us, a linear ordinary differential equation is nothing but a linear operator from CA1AB to CAB. So that means you have already represented your differential equation by an operator that you have denoted by T, and then you are discussing the distance between this C1 AB and other things. So now if the C1 AB already we have discussed, C1 AB is nothing but a Banach space. So now when you are discussing the your ordinary differential equation, this leads to a linear operator between one Banach space C1 AB to CAB. So what I mean to say, that discussing the qualitative properties of a differential equation, now it has reduces to discussing the qualitative properties of a linear operator between two Banach spaces. So now we'll move in that, we'll try to characterize the operator between Banach spaces. Then again, I'll come back to our initial value problem, original problem, right? So now suppose X is a nonlinear space, Y is a nonlinear space, then the operator T is said to be bounded linear operator if it satisfies this condition. So that means T is mapping from X to Y, and T is said to be bounded if norm of Txy is less than equal to this. So in other sense, if T can send a bounded set to a bounded subset of Y, then you call it is a bounded operator. And this condition is basically precisely tells you that if norm of X is bounded, then one can see that T of X will be also bounded. So it's sending a bounded set to another bounded set. So now this collection of all bounded operator is actually a nonlinear space along with this operator norm. So that means if T is a bounded operator between two function space, then the collection is again a nonlinear space, and the norm is given by norm of T by this formula, which is known as a operator norm. And now let us see that some example. So let us consider our operator. So that differential operator T from C1 to CAB, and C1 is having a norm given by 1 infinity, and CAB is having a norm, so that is given by the infinity. Both norms are different, but with respect to individual norm, both are Banach spaces, and you are writing the linear differential equation y dash plus py by this operator, where p is a fixed continuous function. So now one can easily see that this T is a bounded operator. How one can see this is a bounded operator? Just you calculate the norm of T with respect to CAB norm. So what is CAB norm? That is the infinity. So infinity equal to, again Ty is defined by y dash plus py. Again y dash plus py is nothing but maximum of x belongs to this y dash plus py x. Then when you apply the definition of addition of function, that will gives you maximum of y dash x plus px yx. So again, this you apply the triangle inequality. So triangle inequality will gives you this is less than equal to y dash x plus mod of px plus mod of yx. Then you take the maximum of y dash x and yx. So that is exactly the y in 1 infinity norm. So ultimately you will find out a constant capital M denoted by maximum of 1 comma M such that Ty infinity will be less than equal to this. So this operator from C1 to C one can identify as a bounded operator, right? Okay. So in general, a bounded function need not be a continuous. But in case of linear operator, one can see that a bounded operator will be a continuous and then a continuous operator will be a bounded. So if T is a bounded linear operator, then T is continuous. And it is quite easy to verify. So just you see that T is linear, so Tx1 minus Tx2 over y is equal to this. Just you apply the linearity of T. Again, since T is bounded, so you will find some M such that this one will be less than equal to M, x1 minus x2 x. So that basically tells you, this means this quantity you can make less than epsilon provided more norm of x1 minus x2 also here should be x. So there is a typo. So norm of x1 minus x2 x should be less than delta. And what is delta? Delta is basically less than epsilon by m. So that means for given epsilon, you will find a delta such that this condition will always hold. So that means if it is a bounded operator, then it will have a continuous operator. And similarly, the other way is also true. So now, here delta, if you see, depend on epsilon. So it doesn't depend on the x1 or x2. So in other sense, you can say it's sort of a uniformly continuous function. So that means if T is a bounded linear operator, then one can say T is sort of a uniformly continuous function in the sense that your delta doesn't depend on the values of x1 or x2, right? So now once you have a bounded map, this gives you a very useful result in the functional analysis that is known as the open mapping theorem. So what is open mapping theorem? So that tells you that if T is a operator from a Banach space X to a Banach space Y, then if T is onto, then T is a open map. So it tells you that if T is a onto bounded linear map between two Banach spaces, then T is a open map. Open map means it sends the open set to open set. So that's why it is called an open map. And more importantly, so in addition, if T is 1 to 1, so apart from 1 to, if T is 1, 1 bounded between two Banach spaces, then T inverse is also bounded. So that means this one can see as an important corollary of this open mapping theorem. If T is a 1-to-1 correspondence between two Banach spaces, and if it is bounded, linear, then T inverse is also continuous. So bounded means it is a continuous map. So that means it tells you the boundedness of an inverse linear map. So when you can have a boundedness of an inverse linear map, so a sufficient condition is that if T is bounded linear 1, 1 and onto between Banach spaces, then T inverse will be again a bounded or it is a continuous map. And this result is useful in studying the stability of our initial value problem. So what you can do, so just you consider a map T from C1 AB cross this product space by Ty is equal to Q alpha. And how this Y, Q alpha are related? They are related by this initial value problem. So what exactly you are doing? So if you have an initial value problem given by Y dash plus PYQ, YC is equal to alpha, PQ are continuous, and alpha is a real number, then what exactly you are doing? You are mapping the solution space to the data space. So what is your data space? So Q is a data and alpha is also an initial data. So that means this basically you are mapping to a, that means given data. So that means Ty is equal to Q alpha, and then this PQ alpha Y all are related by this initial value problem. Then immediately one can recognize that means T is nothing but a 1-1 map. So how one can recognize T is a 1? Oh, here I have written. Okay, so these are the definition. So first, I have mentioned it is a bounded. So okay, so let us see. That means T one can see it is a bounded map. So the way it has done in the previous example, same thing you can do. So here only the map definition has been changed. So Ty is equal to norm of Q alpha. Again, the product space, the norm is defined by Q infinity plus mod of alpha. Again, Q is nothing but y dash plus Pyy, and already you have proved that this quantity is less than equal to this quantity. Again, Yc is nothing but the value of a function at a particular point. Obviously, it has to be less than equal to its maximum value. So that maximum value you are writing as an infinity norm. So ultimately, you will combining all those norm of Ty, you can write down less than equal to m norm of y 1 infinity. So that means this map you are writing for the initial value problem T, that is a bounded linear map between two Banach spaces C1 and C2. And then one can say that T is 1, 1 and onto. Why T is 1, 1? Because one can see that kernel of the operator Ty. So kernel of T operator T means collection of all y such that Ty equal to 0. So Ty equal to 0 means, that means it is mapping to a 0 element. So what is the 0 element of CAB? That is the 0 function. What is the 0 element of R? That is the 0. So that means Ty equal to 0 means Ty is mapping to 0, 0. The 0 first 0 means that is a function, and the second 0 means that is the real number. Again, already you have, so already you know, that means if Q equal to 0, alpha equal to 0, then Y equal to 0. That observation already we have made from the initial value problem. So that means now when Ty equal to 0, that means Q is 0, alpha is 0, and when Q is 0, alpha 0, then already you have proved that Y equal to 0. So that means the kernel of T consists of only 0 function. So that means it is a 1, 1 function. And then how one can see this is onto function, and that is gives you by existence of the solution. That means if you have Q alpha, then you can always have a solution of this initial value problem. So such that Ty is equal to this. So that means you will basically tells you that T is 1, 1, T is onto, and then T inverse is also continuous due to the open mapping theorem. Because already you have the operator T defined by this relation is bounded 1, 1 onto between two Banach spaces. So due to open mapping theorem, so it tells you that T inverse is a continuous map. And the moment T inverse is a continuous map, so that gives you, so T inverse is a continuous map. Okay, so let us pause for some time. So let us come back to our initial value problem. So what is our original initial value problem? T y dash plus Py equal to Q, Yc is equal to alpha, Pq are continuous function. And this initial value problem you have represented in an operator notation by Ty is equal to Q alpha. And now you consider the Partharp initial value problem, y delta dash plus Py delta x Q. And then this initial value problem you can write in an operator notation, Ty delta is equal to Q minus alpha delta, right? So this you have done. Again, now we apply the continuity of this map, T inverse. So T inverse is continuous. So T inverse is continuous means for given epsilon, there exists an delta, I have written down delta tilde, such that these two conditions are satisfied. So it is purely from the continuity of a linear operator. Again, if you see what is T inverse Q alpha, Ty is equal to Q alpha. So T inverse Q alpha is nothing but Y. Again, T inverse Q alpha delta is nothing but Y delta. So that means this quantity is nothing but norm of Y minus Y delta 1 infinity, which is less than epsilon. And when this norm is less than delta tilde. So what is this norm? So Q minus Q, that will be 0, and alpha minus alpha delta, that will gives you, so sorry, here is a typo. It should be mod of alpha minus alpha delta. So this is less than that. So this tells you that when alpha minus alpha delta is negligible, then this one is also negligible. So that means this tells you that you can make the difference between y and y delta. Not only y and y delta, you can make the difference between y dash and y delta dash negligible when alpha and alpha delta is negligible, and that exactly known as the stability. So what this tells you that if the perturbation is small, then the perturbation of the solution as well as derivative of the solution will be also negligible. And that exactly is known as the stability. So with this, I stop here. Thank you. So
Thank you
Manjil.
so much. Thank you so much, sir, for the very nice talk and for explaining so many things and connecting so many topics in the same talk. Thank you so much. We have several questions, so
Okay.
I'll just give you the questions. Um, so this is a long question. Suppose we are given a finite number of data points and the value of the function in these data points, and then we would like to solve a differential equation. Is it possible to check from the data that the solution will be continuous?
Linear case, it is always possible. If you have a linear problem and if you're given a coefficient function and source function is continuous, then you can always have a uniqueness of the solution. You can always have a uniqueness.
Okay, sir.
So his question was about the uniqueness, right? Existential
No,
uniqueness.
yes. Also, will the solution be continuous? It says.
So, yes, solution, because the moment you have a classical solution, so it has to be, if you are considering the C1, sorry, first order equation, it will be in C1. So C1 means it will be continuously differentiable, so it will have a continuity. But nonlinear case is just looking at the given functions and given data, it is impossible. Unless and until you do not solve the problem exactly, you do not have any idea where it will be of a singularity. But linear case, yes. When the functions are continuous, you have a classical solution, means the solution will be continuous.
Okay,
Linear
sir.
case.
Okay, sir. Sir, there is a question which asks, is the theory for partial differential equations analogous to the theory for ordinary differential equations?
No. There is a complete difference. So what is the difference? When you are talking about the ordinary differential equation, the dimension of the solution space become a finite space. So for example, if you consider a second order equation, then the dimension of the solution space will be 2. If it is nth order, the dimension will be n. But you just simply take a simple first order equation, ux is equal to 0. U is a function of x and y. Then you take any y will be a solution, y square will be a solution, y cube will be a solution. So for a simple partial differential equation, the solution space itself is an infinite dimensional. So the way you handle the ordinary differential equation, you cannot treat a partial differential equation in a similar line. Yes, you can copy some idea, but that may not holds true for a partial differential equation, because straight away dimension space become critical in partial differential equation.
Okay, sir. Sir, there are some questions which are not exactly related to the talk. I'll ask, if you wish, you can answer them.
Just it might happen that I may not also know, but we can discuss.
Okay, sir. So the question is, if you have a method for finding parameters of non-linear systems of ODEs, what would it need to have to be competitive or impressive? Yeah.
Competitive and so okay. So that means if parameter have estimated. If parameters are estimated, then probably you can go for some statistical tools to check the stability. That means which parameter is basically with respect to which parameter stable, which parameter it is unstable. So basically it is an inverse problem. What is inverse problem? For example, you just simply consider a partial differential equation, say heat equation. Yt plus, that means Laplacian of k, ux is uxy equal to some function, right? So now here parameter means that coefficient, that is heat conduction parameter. So what exactly it happens? Will be given a beta so that we can find out the solution. But what he is asking that y is given, that parameter, that means estimation is also done. Then the how parameter is basically that means capturing the real scenario or not. So that exactly it is the study in an inverse problem. So yes, some stability, those things could be done for the inverse problem. So that is a different part that can see for the inverse problem.
Okay, sir. So the next question is how to reduce nonlinear state space model of high relative degree.
So what, can you repeat the question?
How to reduce non-linear state space model of high relative degree?
High relativity.
High relative degree.
High relative degree. Okay, so that means if degree power is very high.
Yes, sir. Yes.
Uh, so exactly, it's very difficult to answer your question. Why it is difficult? Because ultimately, nonlinear problem you cannot solve it directly. So you have to apply some linearization technique, and again those linearization technique problem defined. So that means if some problem is different, then you have to apply some different linearization technique. So again those stability and all those things will be different in each cases. So at one shot it will be very difficult to answer. So that means depending on the problem, you have to come up with a algorithm. That's all.
Okay, sir. Sir, several people have asked, can you give some concrete example of applications of the theory that you mentioned?
Example, see, in case of, I already I said that I would have given some example towards the end, but I found that this is also a very lengthy talk, so I skip that part. Probably in your next presentation, I may go for some applications. There are many applications. So this theory, those who are well aware of the fact your partial differential equation, so they will be knowing all those things. So there are many applications.
Sir,
So
just
probably after your 6 months, I can give some talk.
so just to
Yes.
mention that Professor Swarup Nandan Bora gave one talk a few months back where he gave applications to water waves.
Water wave, yes, yes.
Sir,
So
the
many
next,
applications. But if I take this application, my applications will be not straight away in that way. My applications will be, you have a problem, then the analysis, then the well-posedness, and then how will you implement. That's all.
sir, the next question is every linear map in a finite dimensional vector space bounded? So if the map T from X to Y, where X and Y are both
Okay, finite dimension, yes, it is bounded. Because you can compare the coefficients expressing linear combination, you can compare, so it will be bounded
sir,
in finite dimension.
what techniques are used to prove the open mapping theorem? How is the proof?
Yes, it is. See, functional analysis is based on four pillars. One is principle of uniform boundedness, open mapping theorem, closed graph theorem, and then Harmonic extension theorem, right? So now, this open mapping theorem just it's very non-trivial sort of proof. So exactly what just right now it will be difficult for me all those steps. So simply it map open set to open set. So you can see some standard book also, no issue. There is no shortcut. That means some non-trivial techniques are there.
Sir, let me take the last maths related question, which asks how can I apply these
Okay.
differential equations in mathematical modeling?
Differential and see differential equation in mathematical model. What exactly happens? Ultimately, if you have a real problem, then ultimately you have to solve a set of a differential equation along with certain conditions. Either initial value problem or you have to solve with a boundary condition. If it is a physical problem, bounded domain, so naturally you have to deal with a bounded boundary value problem, right? So now again that boundary value problem solution will be in infinite dimension. So when you approximate, you have to approximate in a finite dimensional setting, and that approximation in finite dimensional setting can be done by many ways. Either you can apply finite difference scheme, you can apply the finite element scheme, you can apply many other numerical techniques. But all the techniques are basically, idea is to represent the infinite setting to a finite setting. That means ultimately you have to solve a system of equation, and then just to apply, when you suppose you wish to see that your method is applicable or not, then what you can do, you just verify your algorithm with some well-known result. Well-known result means there are many research which probably going on your problem, and many experimental data will be available from very reputed journal. So you validate numerical algorithm with the data, perform the all those very good journals, validate your finally from those problems. That is the way it is done.
Okay, sir. Sir, I asked this question to every speaker, so this will be the last question from my side. Can you suggest some
Okay.
books for this topic for the?
I forgot actually. Let me share some another slide. There are some. I have some books. I don't know if I stop this sharing whether I can go
Sorry,
to that
you have
slide or
stopped
not.
it. Can you share again?
Okay, I can share again, right?
Yes, sir.
Okay, okay, I can share. Just a minute. Just you hold on. Let me check. This should be here. Somehow it is misplaced. So now I can tell you those.
So you can tell me and I'll
Hello,
type in the
Manjil.
chat box.
Okay, okay. So now these are basically when you are going for this differential equation, then there are ordinary differential equation. To start with, there is a book called Boy's Diploma. So that book involve OD as well as PD, but OD part you can go through that book. So then when it comes to the partial differential equation, there is a classic book called Partial Differential Equation by Evans. Partial differential equation by L.C. Evans. So that book someone can read, so which discuss the classical theory. And apart from Evans' book, if you someone really want to learn partial differential equation in modern setting, then there is a book called Partial Differential Equation and Functional Analysis for Partial Differential Equation by Franco Vresi. So that book also someone can discuss. And if you wish to learn really go further, then there is a 3-volume book by Professor Lyons. So non-homogeneous boundary value problems. So it is written in French, but English translation also you will get. Elliptic problem, there is a 1 volume, parabolic problem, 1 volume, and then for hyperbolic, there is another volume. I feel someone is interested in doing research in PDE or numerical analysis, they should go through these books. Hello, Manjil.
Yes, sir. Thank you, sir. I have written the names of the book. So we have actually Professor Ajit Iqbal Singh from Delhi in the talk, and she gave some references as well. I have shared the references in the chat box to the students. If Professor Singh wants to say anything, she can.
It is a very nice self-complete talk. Thank you very much, Professor Deka. And I just wanted to bring out that functional analysis began with solutions of linear systems of equations, differential equations, and integral equations. And there's a nice article by my research supervisor. You are Manjil and these people's teacher. My teacher was Dr. F. Smithies at Cambridge. And this article is on the shaping of functional analysis. And he brings out the importance of solutions of systems of linear equations, differential equations, and how functional analysis began. Every good mathematics begins with applications, and then it follows its own path of development into pure mathematics. So we go on like this: applications, then mathematics develops, then applications, then mathematics develops, then applications. So development is like this. And there is a nice article by Lindstrom also, and that also says functional analysis began with differential equations.
Yes, yes.
All these gave rise to this such a rich branch of analysis. And I thank you, Professor Deka, for bringing out this importance in a very nice, clear, self-complete way. Thank you.
Thank you.
So let me, sir, thank you formally once again for giving the very nice talk and for answering so many questions. So thank you so much, sir.
Yes, so kindly please send the references what Professor Iqbal is saying. So just please share those links of those articles. I will be happy to read.
I'll close the live stream now and the recording.